Hello, myself Dr. Shaila Dinkarapte. Today we will discuss Z transform and the properties of ROC, that is the region of convergence. Firstly, let us see what all we discuss in this particular lecture. First one we'll discuss is need for a transform, why transform is required. Then we'll consider the relation between Z transform and Laplace transform, then Z transform and Fourier transform. Then we'll discuss the convergence of the Z transform and the region of convergence. And then we'll finally consider properties of ROC, region of convergence. So firstly let us say why we require a transform. So we have the time domain signal and we are taking the transform. Why we take the transform? The first thing is the spectral properties we can obtain. So transform domain is usually a spectral domain or the frequency domain. And what we are actually doing when we take the transform is we are changing the view of the signal, and the hidden properties, some properties may be hidden in the frequency domain. So these properties may become visible. That is the first advantage of using a transform. Second advantage is once we write down the transfer function of the system, it will have a numerator polynomial and a denominator polynomial. The denominator polynomial has the roots, those are called as the poles, and the zeros are the numerator polynomial roots. So we can find out where the poles and the zeros lie. If the poles are lying on in a particular region, we can decide whether the system is stable or not. So in case of Laplace domain, we say that if the poles lie on the left hand side of imaginary axis, the system is stable. Similarly, for Z domain, we say that if the poles are within the unit circle in Z domain, then the system is stable. The third reason why we take a transform is in a transform domain, the energy compaction occurs, means the energy of the signal gets concentrated in less number of coefficients. So what we can do is discard the coefficients, those are going below certain threshold, and then we can decode, or we can say we can code the corresponding coefficients which are significant. And suppose let us say that if you have the signal which contains 256 points, out of these 256 points, suppose first 50 points are significant, further values are very small, so we discard it. So 256 signal values we can compress it in only 50 coefficients, and these 50 coefficients when received at the receiver end, what you have to do, you have to take the inverse transform and then recover the signal. So for that, the signal, that corresponding transform must be in you can say it must be a revertible transform, so that the signal can be easily recovered from the corresponding transform coefficients. Let us consider the Laplace domain. In case of Laplace domain, we use the complex frequency variable called as S, and this S is written as sigma plus j omega. Now, this complex frequency, people are afraid, students are afraid when they say this is a complex frequency. But don't worry, don't be afraid. No meaning is attached to the complex frequency. It is the mathematical abstraction, right? So don't be afraid of the complex frequency. The transfer function in the Laplace domain is written in terms of this particular variable capital S. If the roots of the denominator polynomial lie on the left hand side of imaginary axis, we say that the system is stable. In case of discrete time signal, we will be assuming that the ideal sampler we are using, ideal sampler means the corresponding sampling takes place only at a particular instantaneous point, and it is done ideally. Similarly, we are considering that the sampling will have to be uniform, in the sense that we are taking the corresponding samples at regular intervals of time. And this regular time interval is what is called as capital T, the sampling interval. And when we write the corresponding signal as Fn, actually it is Fn capital T, and that capital T is usually dropped. Now let us consider the relation between Laplace transform and Z transform. Now for a discrete time signal, this T will be replaced by N into capital T because it is the nth sample, and when we are using uniform sampling, the interval between every two samples is capital T. So we can write Fs as, now we will write it as summation because it is for the discrete time signal. So summation Fn e raised to minus Sn capital T, where the capital T is the time interval between the two samples, N is the nth sample it is representing, and S is the corresponding complex frequency variable. Now here you can see from this formula that the corresponding Laplace transform will depend on capital T. Similarly, if you define the Z transform, if you define Z as e raised to minus S capital T, the Z transform will also depend on this capital T. So it depends on how you sample it, whether you sample it above the Nyquist rate or below the Nyquist rate, right? So when we convert this Laplace domain to Z domain, how we write Fz? Fz will be equal to summation n varying from 0 to infinity if it is a right-handed sequence, Fnt z raised to minus n, because e raised to minus s into t is what is z. So we write it as z raised to minus n. Now relation between Fourier transform and Z transform. Now Z, as you understand, it is a complex variable because it contains S, capital S, which is also a complex number. So the corresponding variable Z will be represented as its real component and its imaginary component. So real part of Z and imaginary component of Z. So we can write Z in the polar form. We can write it as R, where R is the representing the magnitude of the Z, and R e raised to j omega, where omega represents the phase angle. Now in this case we are not using capital T because it is uniform. So F and T will be represented as Fn, as I already told you. So the Fourier transform of Fn into R e raised to minus n is what is called as Fz. See, this Fz we are writing it as summation n varying from minus infinity to infinity Fn R raised to minus n into e raised to minus j omega n, where e raised to minus j omega is supposed to be the phase and this is the magnitude. So what is any signal into e raised to minus j omega n? It is Fourier transform. So this this is Z transform is nothing but it is the Fourier transform of Fn R raised to minus n. Okay, so if I take R is equal to 1, that is a unit circle in Z domain, then the corresponding Z transform will be same as the Fourier transform. So we can say that Z transform reduces to Fourier transform on a unit circle. Now what is region of convergence? The corresponding signal Fn will have its Z transform as given by this particular equation. Now the corresponding Z transform will converge, or it will exist only for certain values of R. The range of values of R for which the Z transform converges is then called as the region of convergence for that particular Z transform. That is also abbreviated as ROC. Now consider one example. Fn is given by 2 e raised to minus 6n minus 2 e raised to minus 3n plus 24 n e raised to minus 6n, and this is defined for n greater than or equal to 0. So if the sequence is defined as existing for n greater than or equal to 0, we say that it is a right-handed sequence. So for this Fn, let us calculate Fz using the formula that we have written down. So Fz will be equal to summation. Now the summation will be from 0 to infinity because the signal is existing from n greater than or equal to 0 onwards. So n is equal to 0 to infinity 2 e raised to minus 6n, this is the signal, into z raised to minus n, minus this is the signal into z raised to minus n, plus this is the signal into z raised to minus n, right. So we can write fz as equal to twice e raised to minus 6 z inverse raised to n, this is minus 2 e raised to minus 3 z inverse raised to n, plus 24 n into e raised to minus z, z inverse raised to n. So whatever we get in the bracket, we write it over here. So how the z transform closed form expression will be written down? We will write fz as 2 1 upon 1 minus whatever is there inside this bracket will be written here. Minus 2 1 upon 1 minus e raised to minus 3 z inverse will come here, and plus 24 e raised to minus 6 z inverse divided by 1 minus e raised to minus 6 z inverse raised to 2. Why this is so? This will come to it when we consider what will be the Fourier transform of nfn. So this is using the property of differentiation in z domain. So this will come to it later. Now when the corresponding function is existing for n greater than or equal to 0, then we can find out what will be the ROC. Now whatever is there inside the bracket in the denominator, we have to put mod of that less than 1 to find the ROC. So this indicates that mod z should be greater than e raised to minus 6. For this term it should be mod z greater than e raised to minus 3. So whichever circle is farthest, which is having the bigger radius, that is z greater than e raised to minus 3, this will be called as the ROC of the corresponding z transform, and this form that we have written down is what is called as closed form of the z transform. This is the ROC that we have specified. This is the real part of Z, this is imaginary part of Z, and we draw a circle in Z domain with radius equal to e raised to minus 3, and we show the area that is outside this circle as the area of convergence or region of convergence. So this is a diagram representing ROC for the corresponding Z transform. Now how to get this closed form expression for Z transform? So let us consider that xz is given by 1 plus az inverse plus a square z raised to minus 2 plus a cube z raised to minus 3 and so on. So this is existing from n equal to 0 to infinity. Now what we will do is we will multiply this equation 1 by az inverse and then subtract it from this equation 1. So what we have? We have is 1 minus az inverse into xz, because we are multiplying this equation by az inverse and subtracting it from equation 1. So you will find that this az inverse a square z raised to minus 2, a cube z raised to minus 3, all these in between terms will cancel and you will have 1 minus a raised to infinity z raised to minus infinity remaining. Now we can replace this a raised to infinity z raised to minus infinity by 0 provided a is less than 1, right. So if a less than 1, then we can say that a raised to infinity will tend to 0, and in that case I can just write this xz as equal to 1 divided by 1 minus az inverse. So whatever is this az inverse, this is written in the denominator inside this bracket, 1 minus the same term will appear. This is what is called as closed form expression. Now to find the ROC, we will have to equate this term less than 1. So what is the value? Mod z must be greater than mod a. But in that case a must be equal to less than 1. So if we are plotting the ROC, we'll have to plot it on the same lines, but in this case the radius is equal to mod A, the radius should be less than 1. Then only it will be converging, otherwise the system corresponding Z transform will diverge. Now consider the right-handed sequence. See, let us say consider Fn is equal to cos of n omega t un. Un indicates that it is existing between 0 to infinity. Now we can write fz as summation n varying from 0 to infinity cos n omega t z raised to minus n as per the formula. So what is cos n omega t? It is 1 half e raised to n j omega t plus e raised to minus n j omega t by 2. So I am replacing the corresponding value of cos and I get this term. Now what I do, I take 1 half as a common factor and I'll write the closed form expression for this. What is the closed form expression for this term? It will be 1 upon 1 minus e raised to j omega t z inverse, because I'll have to write this as e raised to j omega t z inverse raised to n. So whatever is there inside the bracket, that is e raised to j omega t z inverse, will be written in the denominator. Similarly, for the second term, we write 1 upon 1 minus e raised to minus j omega t z inverse, right? And we just simplify this to get this particular answer. Now, in this particular case, the first term converges when e raised to j omega t z inverse is less than 1, means mod z greater than 1. Why? Because magnitude of e raised to j omega t is nothing but 1. Similarly, e raised to minus j omega t z inverse is less than 1 for the second term. So again, mod z should be greater than e raised to minus j omega t magnitude, that is equal to 1. So what is the region of convergence? Mod z greater than 1. So how we draw the region of convergence? It is the area outside this circle, unit circle in Z domain. What is a unit circle? The circle with magnitude equal to 1 is called as the unit circle. Let us consider one more example. This is a little tricky. Yn is summation k equal to minus infinity to n xk. Now, how we write it? What I will do is, I will take yn minus 1. So what is yn? Yn is this summation minus yn minus 1 will be k varying from minus infinity to n minus 1, because I am writing for yn minus 1 xk. Now what is this? In this case, summation from minus infinity to n minus 1 will be getting cancelled with the first term, and I will have only xn remaining in the first summation. So yn minus 1 is equal to xn. Now what I do, just take Z transform on both sides. So Z transform of yn minus 1 is equal to Z transform of xn. So after simplifying this, what is yn minus 1 Z transform? It will be Z inverse yz. Why Z inverse yz? Because there is a delay of one sample. This delay will be reflecting as Z inverse yz. So I can get yz is equal to xz upon 1 minus Z inverse. Such tricky examples you must be in a position to solve. Now let us consider what are the properties of ROC. The ROC of xz consists of a circular ring in the z plane centered around origin. This is obvious, as we have seen the ROCs, those are plotted. It consists of a ring. Why it consists of a ring? Because we are defining z is equal to r e raised to j omega. So what is this? We are writing this as the real part, that is r is the magnitude part and e raised to j omega is the phase part. So ROC consists of the region of values of z for which x and r raised to minus n is absolutely summable. So the convergence depends on mod z equal to r, and it does not depend on the angle, because we have to find that whether x and r raised to minus n is convergent or not. It does not depend on e raised to j omega. That means it does not depend on the angle at all. So ROC will definitely consist of a ring. The ROC does not contain any pole, obviously, because ROC means region of convergence. How the region of convergence will contain the poles? At the pole location, what happens? at the pole locations, the system goes to infinity. That means the system diverges. System function diverges. So, if the system function diverges, it cannot be included in the region of convergence. The third property, if the sequence xn is of finite duration, then ROC is the entire z plane except possibly z equal to 0 and or z equal to infinity. So, let us consider the corresponding xz summation xn z raised to minus n, and let us say that it exists between n equal to capital N1 to n equal to capital N2. That is a finite duration sequence. If n1 and n2 are both negative, then z raised to minus n. Now n is varying from n1 to n2, but both are negative. So z raised to minus of minus n1, n1 is negative. So it will contain all positive powers of z. The z transform will converge for values which are less, but z transform will diverge at z equal to infinity because it contains all positive powers of z. So z raised to infinity will diverge obviously. So ROC will not contain z is equal to infinity. Now consider n1 and n2 both are positive. Then in that case it will include all negative powers of z, and z transform will diverge for z equal to 0. So when z is equal to 0, means it is tending to 0, z raised to minus n, in this case because it is containing negative powers of z, it will diverge. So ROC will exclude z is equal to 0. If n1 is negative and n2 is positive, xz will contain both positive as well as negative powers of z. That means it will diverge for z equal to 0 and for z is equal to infinity. So as it says, except possibly z equal to 0 and or z equal to infinity. This and is holding good when n1 is negative and n2 is positive. If n1 and n2 both are negative, then in that case it excludes z equal to infinity. When both are positive, it excludes z equal to 0. Now let us consider one example that will illustrate this property. If xn is a raised to n between 0 to capital N minus 1, here n1 is 0 and n2 is n minus 1, and it is a positive value. So as per our property, ROC must include z equal to 0. So let us say xz is equal to 1 plus az inverse plus a raised to 2 z raised to minus 2 and so on, and it will exist only up to a raised to n minus 1 z raised to minus of n minus 1 because we are specifying this value of n2. Now multiply by az inverse and subtract from equation 1 to get the closed form expression. So we can write xz as equal to 1 minus a raised to n z raised to minus n divided by 1 minus az inverse. Now in this case this term is existing. It is not going to, n is not going to infinity. So this term will be there. Now if we simplify, we will have z raised to n minus a raised to n divided by z raised to n minus 1 multiplied by z minus a. This we are obtaining from this equation by multiplying numerator and denominator by z raised to n. So we get the closed form expression in this manner. Now a pole at z is equal to a, that is this particular root, will be cancelled by the 0. So in the numerator also we have z minus a term. It will cancel with the z minus a. That means the pole and 0 at z is equal to a will get cancelled. But the system will have a pole of order n minus 1 at z equal to 0. That means ROC will exclude z is equal to 0. Here it is, I am sorry, it should be written as ROC will exclude z is equal to 0. So in this case we are drawing the region of convergence like this. It is the area outside this circle with radius equal to a. In this case there is a pole of order n minus 1 at z equal to 0. There are zeros elsewhere, but the 0 at z is equal to a is cancelled by the corresponding pole. Now let us consider properties of ROC. If Xn is a right-handed sequence, that is, it is a causal sequence. Why causal? Because the signal samples are existing from n equal to 0. It may go up to infinity or it may be a finite duration, but it will be causal in that case. And if the circle mod z is equal to R0 is in ROC, then all finite values of z for which mod z is greater than R0 will also be in ROC. Because in this case it is a right-handed sequence, so xz will contain all negative powers of z. So if z is equal to 0 is in ROC, xn r raised to minus n converges. Now if z is greater than r0, suppose we consider a circle which is having the radius which is greater than r0, then in that case xn r corresponding r raised to minus n will also converge. It will converge more rapidly because the corresponding radius is higher. So the values of z for which it is greater than r0 will also be in ROC. So this is the region of convergence. If the radius is R0 is in region of convergence, suppose I draw the circle which is having the radius which is greater than R0, then it will be included in the ROC. Next property of ROC. If Xn is a left-handed sequence and if the circle mod z is equal to R0 is in ROC, then all finite values of z for which mod z less than R0 will also be in ROC. Now in this case Xn is a left-handed sequence, so Xz will contain all positive powers of z. So in this case, if mod z equal to R0 is in ROC, Xn R0 raised to n will converge. Now if mod z is less than R0, then it will converge more rapidly. Let us see the region of convergence. This is r equal to r0, radius equal to r0. If I draw a circle which is having the radius less than r0, then it will be obviously in the region of convergence. Now the sixth property of ROC, if Xn is a both-sided sequence and if mod z is equal to R0 is in ROC, then ROC will consist of a ring which includes z is equal to R0. Now for a right-handed sequence, as we have understood, the region of convergence is the area which is outside z is equal to R0, and for a left-handed sequence it will be the area which is inside the circle with mod z is equal to R0. Now if you want that the common area of convergence exists for the left-handed sequence and the right-handed sequence, then we will have to see that the corresponding radius for which it is converging, outside the radius for which it is converging, the outside radius should be R1 and the inside radius for which it converges should be equal to R2. So in this case the overlapping area must exist. See, refer to this diagram. Now in this case the right-handed sequence exists outside this circle with radius equal to R1, and the corresponding left-handed sequence converges for the area which is inside this radius R2. So what is the region of convergence? It is a ring consisting of the values of R between R1 to R2. So it consists of a ring. Let us consider one example to illustrate this particular property. So let us consider Fn as b raised to mod n for b greater than 0. Now we can write Fn as equal to b raised to n un, because mod n can have values b raised to n and b raised to minus n. But when it will be mod b raised to n, when it is appended by un, that is between 0 to infinity. And for values, negative values, it will be b raised to minus n, u minus n minus 1. That means this u minus n minus 1, this is existing below corresponding minus 1 to minus infinity. So let us write fz as equal to summation n varying from 0 to infinity b raised to n z raised to minus n, and for this we write minus infinity to minus 1 b raised to minus n z raised to minus 1. Now for this I can directly write down the closed form expression 1 upon 1 minus bz inverse. Now this summation, if I change the limits for n equal to 1 to infinity, I will have to change the corresponding uh, power sign. So I will have to write it as b raised to n z raised to n. Again this n is equal to 1 to infinity, I will write it as summation n varying from 0 to infinity and then minus 1 which is existing for n equal to 0. So for this again I can write the closed form expression 1 upon 1 minus bz, it will be minus 1. So the first term converges for mod z greater than b, that is mod of bz inverse less than 1 means mod z greater than b, and the second term converges for mod z less than 1 by b. The common area of convergence will exist only if b is less than 1. So if b is less than 1, this corresponding circle radius will be greater than 1, and in this case it will be less than 1. So in that case only there will be a region of convergence. The area for the right-handed sequence to converge will be the area outside this radius equal to b, which is less than 1 as we have said, and this radius for which it is the left-handed sequence converges is the area inside this circle with radius equal to 1 by b, b being less than 1, this will be greater than 1, and in that case the common area will exist, and this will be the region of convergence for the first term as well as the second term. Right, in this case if b is greater than 1, then in that case if b is greater than 1, this radius will go outside and this radius 1 by b will come inside, and there is no common area of convergence, right.